Hello guys, welcome back to TechDose, and in this video we will look at largest color value in a directed graph problem, which is from Leetcode number 1857. Let's now look at the problem statement. There is a directed graph of n colored nodes and m edges. The nodes are numbered from 0 to n-1. You are given a string colors where color set I is the lowercase English letter representing the color of the ith node in the graph. That means you will have 26 unique colors ranging from A to Z. You are also given a 2D array edges where edges at j denoting aj bj indicates that there is a directed edge going from aj to bj. A valid path in the graph is a sequence of nodes x1, x2 and so on till xk such that there is a directed edge from xi to xi plus 1 for all the I values ranging from 1 to less than k. The color value of the path is the number of nodes that are colored the most frequently occurring color along the path. Return the largest color value of any valid path in the given graph, or -1 if the graph contains a cycle. Okay, now let's look at the first example. In this example, we need to find a path which has the maximum number of same colors. Okay, what do I mean by that? Let's say if you try to find a path starting from 0, this is one valid path. Okay, this is one valid path 0 2 3 4. So if you think what are the colors, so the colors are already mentioned here. The color is A, B, A, C, A. In this path from 0 to 4, A is occurring 3 times, C is occurring exactly 1 time. So which one is occurring most number of time? This A is occurring most number of time. If you look at another valid path 0 to 1, then in this case 0 are all the node values. The color value is A is occurring 1 time and B is occurring 1 time, right? Here is a B and there is a A. So these are only 2 valid paths. By valid path I mean that it is a cyclic path. In the first path, if there was a cycle like this, then this will not be valid. Okay, a valid path is said to be starting at U and going till V, having any number of nodes in the middle where there is no cycle at all. There shouldn't be any cycle, right? So in this entire graph we should not see any cycle. So the first goal of the entire program should be to do cycle detection, because if there is a cycle then I will always return -1, because it will not be possible to have a cyclic type of path. Okay, all the path must be acyclic. So first thing you do is cycle detection. Now the second goal is to find the maximum number of colors, maximum number of same colors in a path, right? That you have to track. So from 0, what you can do to track the maximum number of same colors? You can simply apply a DFS technique, right? So if you apply a DFS technique from 0, let's say that you are going to 1, then what is the DFS depth? You can go maximum till 1 and again you have to return back. So if you do DFS in this path, you will calculate that A is occurring 1 time, B is occurring 1 time. So in this entire valid path, you have maximum of these two value coming as 1. If you try another path, then you will go from 0 to 2, 2 to 3, 3 to 4. And in this case as well, the A count will be 3 and C count will be 1. So the maximum of these two will be 3. So out of all the valid paths, I don't care which color you are taking, but whichever one occurred the maximum number of times is going to give you the answer. So in this case, A is occurring maximum number of time, which is 3 times in a path from 0 to 4, and that is why the answer is 3. So I think this is clear. Now if I just change this input and say that this is 3 and this is 0. Now we know that all the nodes will range from 0 to n-1. So here n value is equals to 5. So 0 to 4 will be the value for all the nodes. Now if you apply the DFS approach, then you will first try DFS from 0. And if you try DFS from 0, you cannot move back to 2, but you will only move forward to 4. And so you will see what are the color marked. This is A, B, A, C, A. So you will find that if you apply DFS on 0, then C is occurring 1 time and A is occurring 1 time, right? So what is the maximum? Maximum is 1. Again, the next time when you apply DFS, you will be applying at this 1. So you cannot move to any other node. So when you apply DFS at 1, then you will be saying that B is occurring exactly 1 time. So the maximum is 1 here. Then you will be applying DFS on 2. Okay, DFS on 2. So if you apply DFS on 2, then you will be covering these 3 nodes, and you will say that A is occurring 2 number of times, C is occurring 1 time, and the maximum is 2. And likewise you will continue to do DFS from 3. So if you do DFS from 3, then you will find that A is occurring A is occurring 3 times, C is occurring 1 time, and then B is also occurring 1 time. Because if you follow this path 3 2 0 4, then A is occurring 3 times, C is occurring 1 time. Okay, and if you follow another path A B, then in this case A is occurring 1 time and B is occurring 1 time. So out of these 2 paths, you can take the max occurrence of A, max occurrence of C, max occurrence of B, and take the max of it, which is 3. Again you will have to try DFS from 4, and if you apply DFS from 4, there is exactly 1 node and the color is A. So A is occurring exactly 1 time and the max value is 1. Throughout all the maximum values, you take the max as an answer. So 3 will be the answer in this particular case. So if you try to perform DFS from all the nodes, then we know that already DFS algorithm takes V plus E time. And in this case, the number of nodes are n and the number of edges are m. So you can say that order of n plus m time. Both of them in the constraint section, it is given 10 to the power of 5. Okay, 10 to the power 5 size input. So this time is taken for only one DFS call. And we are trying to do it n number of times because we are doing it from each node. So this will be multiplied with the value n. And so you can imagine that this is going to be n square plus mn. And you know this n square is going to be 10 to the power of 10. So if we have to run it within 1 second, 1 second standard is 10 to the power 8 computations. So this will definitely give you TLE. The maximum number of operations that we do must be less than 10 to the power 8 computations to get accepted. Okay, so this kind of algorithm is not going to work, right? So what should we do? If you look at this problem carefully, when we had already done DFS for 0, then I had the count of C and A with us, right? So when we are applying DFS at 2, this is calling DFS on 0 again. So instead of making another DFS call, because you will again be getting the same exact count, C equals to 1 and A equals to 1, you can save this result and return back optimally. Okay, return back optimally in such a way that 2 does not have to explore the entire subgraph which is going through this 0. Instead of that, whatever 0 had already calculated, just return it back. Okay, and the same concept will be used when you apply DFS for 3. When you apply DFS for 3, then this entire solution is already made, because DFS for 2 is already calculating that A is occurring 2 times and C is occurring 1 time. So instead of parsing through the entire subgraph through 2, whatever the result stored at 2, you just return it back to node 3. And what is this technique called? If you save the past calculated results, past subproblem result, which you will be reusing, then that technique is your dynamic programming technique, right? So this entire problem constitutes of cycle detection technique, and second thing is dynamic programming. So I hope you are clear with what things we have to use in this particular case. Just to go over the constraint, n is the number of nodes, m is the number of edges, both being maximum 10 to the power of 5, and the colors has all the English letters, so you can say 26 colors can be present at maximum. So let's now look at the goals. So I will just be recapping that the first goal is to do cycle detection, and there are multiple techniques to do that. In this case, we are taking a directed graph. In directed graph, you can go with the BFS technique, which is topological sort. You can use the Kahn's algorithm, okay, for the BFS technique. With the DFS technique, you can also go with the DFS topological sort, or otherwise you can go with the 3-color technique, which is a simple DFS, right? So in this problem, we will be going with the DFS 3-color technique. Now the second goal is to remember the maximum length for each color starting at each node, as I had shown you, and we will be doing it with the help of dynamic programming. So this entire problem will be solved as DP on graph, right? I think it is clear for you. Now let's just recap why 3-color cycle detection is needed. So if you remember, I said that we need 3 states or colors to detect cycle in a directed graph. I have given you 2 examples. try it with two colors. If you try it with two colors, then you will have 0 or 1 state which says about unvisited node or visited node. So initially I will mark everybody as unvisited, and let's try to visit them. So if you try DFS from 0, it will be 0, so I will be setting it to 1. Go to 1, I'll be setting it to 1. Go to 2, I'll be setting it to 1. Go to 3, I'll be setting it to 1. And then again you see that an adjacent node is present 1 where it is already visited, so it will say it is cyclic, and yes, it will be able to find the cycle. That is fine. But in the other case, in the second example, if you set everything as unvisited and start the process, then from 0 you will set it 1. From this 0 you will set it 1. From this 2 you will set it 1. Here you will set it 1, right? But from 3 there is no outgoing edge, so you will be backtracking. When you backtrack to 2, then again there is no other outgoing edge, so you will be backtracking to 1. From 1, if you see this 3, then it will say that it is visited, so it will try to assume it like a cycle, but it is not a cycle, right? It is not a cycle. And this happened because we are visiting an already visited node, and we could not find a cycle through 3. So how are we expecting it to be in a cycle, isn't it? So 2 color is insufficient in case of a directed graph. 2 color will be sufficient in case of an undirected graph, okay? But in case of directed graph, you should remember, I should be able to differentiate between this state, visited and processing versus visited and processed. In the first example, when we saw this one via 3, then 1 was visited, but it was under the chain, under the same chain, right? So this will be marked as visited and processing. But once you backtrack, then the backtracked node will be marked as visited and processed. Okay. So that is why if you use 2 colors, then in the first example you will get cyclic as output, and then the second example as well it will say cyclic, even though it is a wrong answer. But if you go with the 3 color technique, let me just show you quickly, then you will be marking everything as unvisited initially, and whenever you visit it for the first time, you mark it as visited and under processing. Mark it as visited and under processing, visited and under processing, visited and under processing. And when you see an edge through 3 to 1 and you see the value 1 here, this means it is creating a cycle because it is still under processing, right? So it will answer cyclic here. If you look at the second example, if I just set 0 values everywhere, and if you start at this node 0, then I can mark it as visited and under processing, visited under processing, visited under processing, and visited under processing. Now from 3 there is no other outgoing edge, so if I have to backtrack, before backtracking I will be setting it to a value 2, saying that it is visited and it is processed, and I could not find a cycle, so I am backtracking, and I am backtracking to 2. Now from 2 there is no other outgoing edge, so I will set to 2, visited and processed, and I'll go to 1. Now from 1 there is another outgoing edge to 3, but if you look at this 3, it is saying state 2, which means it is already visited and we could not find a cycle through 3, so we backtracked already from 3. So this is not in our cycle, so don't explore through this node. Don't explore through this node. And that is why we will still be backtracking from 1 and setting it 2, and we'll be backtracking from 0 setting it 2. So we have covered all the nodes and we could not find cycle, so this will be answering it acyclic. So this is the right way to solve cycle detection for directed graph. We must use 3 colors. For undirected graph we can go with 2 colors. Okay, so this was just a recap of cycle detection. So our first goal is clear. How to do cycle detection? We will be doing it using the DFS 3 color technique. Okay, it is simple to implement. Now the second thing, how to remember the maximum length of each color starting at each node. We will be applying DFS, and with DFS we will try to do dynamic programming. So let's see how to remember the longest path for per color from each node. So I have taken an example here. If you see, for each node I will be assuming that maximum colors are only 3 colors, but in reality you have from small a to small z, there are 26 colors, right? But for example I am taking only 3 colors as maximum. Now if you think about starting from 2, if you start all the paths possible from 2, what are all the possible paths from 2? It is 2, 3 and it is 2, 4, 5. These are only all possible paths. In the path 2, 3 you have A and C. That means A count is 1 and C count is 1. In this path 2, 4, 5 you have 2 as A, 4 as C and 5 as C. So you have A count 1 and C count 2. Okay. Now B count is 0 in both of them. B count is 0 in both of them. So what is the maximum ABC count? Like maximum all the color count for this node 2. If you see for A, it is 1 here, it is 1 here. So for A, I will be saying that at node 2 it will be 1. For B, it is it is 0 count if you follow the path this 2 3, and it is still 0 count if you follow the path 2 4 5. So that is why I will be storing 0 here. For C, if you follow the path 2 3, then C is 1 count, but if you follow the path 2 4 5, then C is getting 2 count. So I will be getting the max of these two and I will be saving it here, right? So this is what I will be saving per node. That means if I have all possible colors as only ABC, that's what I'm assuming, then at a particular node I have to store, if you follow any path, you can follow any directed path without cycle, then how many maximum number of times a color can happen, a color can occur, and this is that answer. A can occur maximum 1 time, whatever path you follow, and each path must be independent of each other. That means 2 3 will be independent of 2 4 5. They must not be added, they can be compared only. Okay, so you can use the max function to compare, and that is how we have calculated. I hope this is clear. I have again given another example for node 1. For node 1, what are all possible path? One possible path is going 1 0 2 3, and in that case the C count is going to be 2, the B count is going to be 1, and the A count is going to be 1. Okay, 2 1 1. Now there is another path which is going to 1 0 2 4 5, and in that case the A count is going to be 1, B count is going to be 1, C count is going to be 3, and there is another path which is going to 1 7, where it is saying C count is 1 and B count is 1. Now if you see which path is giving me the maximum A count, 1 1, and here it is 0, right? The 1 7 is having A count 0. So what is the maximum A count? 1. So that's why I will be saving 1. That means if you have the luxury of choosing whichever path you want starting at 1, then you cannot get more than 1 A color. Fine. Now what will be the B value? So the B value here is 1. Here you have 1, and the third path has 1. So B max value is 1. If you find the C max value, here you have 2, here you have a 3, and another one is 1. So out of all these three values, the maximum is 3 if you follow 1 0 2 4 5, and that is why C will be 3. So these are the values that I will try to track. Now how many nodes are present? You know there are n number of nodes. And how many colors are present? You have A to Z colors. So per node you will require 26 different values to be managed. So if there are n number of nodes, then can't we say that we will need 26 times n number of values to be managed? Right? We have to do that. And for that reason, we will be taking a longest two-dimensional table of size 26 by n, and I will be marking all the values with 0 in the table initially, saying that initially none of the colors are occurring. None of the colors are occurring. So I will be taking the colors on the x-axis, okay, and on the y-axis I have the node. So if I can represent this state for node 2, then I will be taking column number 2 and I will be filling 1 0 2 for it, saying that if I start from 2, then A can occur maximum 1 time whichever path you take, B can occur 0 times whichever path you take, and C can occur maximum 2 times whichever path you take. Okay, I don't care about the path, but this is the maximum count of colors. Now if I have to return a result, then it will be the maximum of this entire column, isn't it? But what this problem is asking, given the graph, you have to just choose a point. You can start at any point. You just have to return the longest count of colors which are repeating in a path. So that will be the maximum in this entire matrix. Maximum in this entire matrix. Okay. So I hope this is clear. Again, I will repeat that if the longest at ij is equals to x, then this means x is the longest length for color I, because I is on the row side, which is the color, starting at node j, because these are all the starting points. Okay. And the point to note is any color can give the longest path. Therefore, maximize the length using all possible colors at each node. Fine. In this case, what is the maximum length? The maximum length is 3, and for which color it is occurring? It is occurring for C. And where it is starting? It is starting at node 1. So starting point can be present at any node, and any of the color can give you the max value. So that will be tracked by tracking the maximum of this entire table. So I hope you have got the idea of how we are trying to apply dynamic programming using the DFS approach, right? So let me give you a dry run. Now let's see the dry run by using the same example. So in this case I am taking a longest 2D matrix which is having 26 number of rows for all the possible colors, but for this example I will just be assuming that I have only 3 possible colors ABC, and the columns, which is n number of columns, where each column will be representing the maximum count of each of the color for each particular nodes. Okay, and initially all the count values will be 0, as I have already explained. Now I will be starting a DFS call from 0, right? Now before making the DFS call, you should know that if you don't want to reprocess the node, you should take a visited array. And also to do the cycle detection, we will be using the 3 color method. So initially all the states will be marked with 0, saying that they are unvisited, as I had already explained, right? They will be unvisited. Whenever you visit a node, you will check the state. If it is 0, then you can process the DFS. So you mark it as visited and under processing. Okay, and you are at 0 now. Now from this 0, you try to make further DFS calls. So from 0, you will try to make a DFS call to 2, change the state to 1, that means visited and under processing. From 2, let's say that you try to make a DFS call to 3 and you change this state to 1, that means visited and under processing. Now from 3, there is no other outgoing edge, and so you need to backtrack from 3. But before backtracking, you have to also make an update to the color. So for this 3, you need to add a count for this color C, because the color is C here, right? So I will be adding one color, so it will be updated by one more value. It will be adding one more value, and then we will be backtracking. So before backtracking, I will be changing the state to 2, that means visited and processed. And now I will be reaching to 2. When you reach back to 2, then you need to update the color count for all of these ABC, because the count you got via 3 may have been more than what you already know. So yes, it is already more, because if you compare the A count, it is 0, B count is 0, but C count has increased by 1, so let's make it 1. Okay, and now you explore the other path. So from 2 you can go to 4 and change the state to 1. From 4 you can go to 5 and change the state to 1, that means visited and under processing. At 5 you do not have any other outgoing edge, so you need to backtrack. Before backtracking, you update the color at 5. So 5's color is C, so let's update, that means add 1 count to the color C. So to row number C and column number 5, you do +1. And before backtracking, you set the state to 2, that means visited and processed. And now your control is back to 4. Now at 4, maybe you will get more count of the number of colors if you take the path via 5. So you will have to update it by looking at the color count at 5. So the color count for 5, for the color A is 0, for color B is 0, but for color C it is 1, that means you have to update this to 1. So that if you take the path via 5, you will get 1 count of C. Now before backtracking, you have to also update the color present at 4. So the color present at 4 is C, so add one more color count to C, which makes it 2. And you backtrack. So before backtracking, you have to also set the state to visited and processed. And now you go to 2. Now once you have explored another path, then again you have to update these values as 2, because maybe via 4 you might be increasing the count of one or more of these colors. So compare these 2's count with the 4's count, and this is 0, 0, 2, this is 0, 0, 1. So which will get updated? This one will get updated to 2, because I want to maximize the count, right? And now we are done. Now through 2 there is no other path. So before backtracking, you have to add this color A to 2. So the color count of A will increase by 1. And before backtracking, you have to set this state to visited and processed. So I have marked it as 2 and I am going to 0. Once you reach to 0, then you need to update the color count of ABC going through 2. You can say via 2. So at 2 you have 1, 0, 2. This is 0, 0, 0. So update it to the max values 1, 0 and 2. and just before backtracking you see the color is B, so update the color count for B and then you backtrack. So before backtracking set the state to visited and processed and you are done. So you are done with the DFS call from 0 and you have updated the color count for 0, 2, 3, 4, 5. Now you don't have to reprocess it again because it is already processed. Now the next time if you are using a for loop for making the DFS call, it will start at 1. Now at 1 your state is 0, make it 1, saying that visited and under processing. Now you will explore all possible path. From 1 you will explore 0. But 0 is already visited and processed. So you must have all the count values, maximum count values for each of the color for all possible path going via 0. So you have that count 1, 1, 2. That is why you can just look up this count and try to maximize the count value here, which will be max of 101, max of 101, max of 202. And then you are done with this exploration. Let's explore another path to 7. So yes, I can go to 7, mark it as visited and under processing. And from 7 you do not have any other outgoing edge, so you need to backtrack. Before backtracking you have to add this color to 7, so it will increase the count of B color by 1 and then you backtrack. Before backtracking again set the state to visited and processed and you backtrack to 1. Again you update the count at 1 by looking at 7 because maybe you will get higher color count of any of these or maybe more going via 7. So update. Max of 1, 0 is 1, max of 1, 1 is 1, max of 2, 0 is 2. Now before backtracking from 1, because there is no other path, you need to update this color C at 1. So this makes it 3. This makes it 3, right? And then you backtrack. First you set the state to 2, that means visited and processed, and you backtrack from 1. Next time the DFS call will come at 2. And 2 is already visited and processed, so nothing is going to happen. Same goes for 3, same goes for 4 and same goes for 5. But when the call is made for 6, then yes, another call will be made and 6 is unvisited, so mark it as visited and under processing. Now there is an outgoing edge to 4, go to 4. But 4 is already visited and processed, so whatever is the value stored at 4, it already has the maximum color count. So just look at this 002 and update at 6, 002. Maximize all the color counts, right? Now you do not have any other outgoing edge, so before backtracking update the color A, so this becomes 1 and you set the state to 2 and you backtrack from 6. The next time DFS call will be made to 7, but it is already visited and processed and there is no other node to be explored. So after exploring all the nodes, whatever is the maximum in this entire matrix will be your answer, which is 3 in this case. Therefore, the maximum color count you get is 3 for any valid path. That means any directed path which is not having a cycle. So this is how we are going to solve it. Now in this particular process, since we are doing the optimal DFS call, so it is going to take V plus E time. And in this case, the number of nodes are n and the number of edges are m, so it will be n plus m. And the space complexity will be n plus m for the adjacency list that we create and 26 times of n for the DP table, right? And you can just assume it like n plus m. So this is the entire time and space. Let's now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. In this problem, we are given the colors and the edges. So first of all, I will be finding the number of nodes by taking the color size and then defining an adjacency list. So this is how I will build the adjacency list, a directed graph. After that, I will be taking the DP table of size 26 by n, and as I have already explained, the longest DP table is a table to store the count of each color from a given node, and if the longest at ij equals to x, then there are x number of I color nodes from current node j. Okay. After this, we will be performing the DFS from each node and maximize the color length. So the max color length will be assumed to be 0 initially, and the visited will be having 3 colors 0, 1, 2. As you know, 0 will be unvisited, 1 is visited and processing, and second is visited and processed. Now after this I will try to make DFS call starting from each of the nodes. So this is a for loop for doing the DFS, and in each of the DFS call I will be taking the return value. If the return value is integer maximum or infinity, then this means that we have found a cycle. So this is doing cycle detection side by side and trying to maximize the maximum color length. Okay, so if the return value is integer maximum, then I'll return -1. That means if there is at least one cycle, then I will say it is not possible to get the answer. Otherwise, if it is not cyclic, if you get something less than integer maximum, then I will be trying to maximize the color length by getting the return value simply. And finally return the max color length. Okay. Now let me show you the DFS function. So in this case, if you look at the DFS function, we are taking the current node adjacency list, the visited array, the longest DP table, and the string colors. So if the current state is 1, that means we have found a cycle and you return integer maximum. Otherwise, if it is 0, then we are visiting it for the first time. Okay. So if we are visiting it for the first time, then we have to mark it as visited and under processing, and after that you explore all the adjacent node. So for each of them, try to make a DFS call and get the return value. If you find a cycle, you return integer maximum. If you don't find a cycle, then try to maximize the color count for each of the possible 26 colors, right? And once you are done with all the neighbors, then before backtracking, you have to increment the color with that particular current node's color and set the state to 2, that means visited and processed, and then you are done. Okay. And finally we need to return the count of that particular color with starting from that particular node. Okay. So this is the entire approach, and I hope it is clear. If you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. See you guys in the next video. Thank you.